So you said, because I used to secant x, so that's fine for me to use.
Yes, as long as it, that's what his question was. So if it's a case one was the secant was square, secant was even, and case two was tangent is odd, right?
Yeah.
So they both were true.
Yeah.
So if you took it, you went about using it in the case two format, you'll still get the same answer as the other people, it just might look different.
Okay.
Because, for example, I might come up with an answer of cosine squared, and you might come up with an answer of 1 minus sine squared. It's the same thing, right? So it's just,
Yeah.
it'll look different in the final answer. So that was why he asked that question, because both those cases were true.
Yeah.
I didn't work it out with the secant, I don't know if it was messy or not, but the tangent one was really quick.
Okay.
Was the secant one messy?
Yes.
Yes?
Yeah.
So now
All
what-
you better call it a secant and a tangent to get secant tangent x. And that's what it is to not be a tangent.
Yes.
So for the blue one, if you put the tangent, then you just left extension, right?
For both of them, the u equals tangent would have been fine.
Oh, okay.
Yes.
Could you actually show like how they would equal each other? Like if you did the answer to one and then have the answer to the other?
I could, but let me do it after the break, because I've got to look and see, I haven't worked it out the other way, so I'd rather have it done quick instead of spending time right now. But yeah, I can show you that. The good news is you guys are asking great questions, which means you know, most of you, I think, know what you were doing and how to approach that. Other questions about the quiz? Remind me after the break to do that, okay? Okay, so if you haven't noticed, I'm wearing one of my favorite shirts today. This is the shirt that I wear on days when the content gets a little more challenging. We already thought it was hard, today gets a little bit harder. We're doing section 7.3 on trig substitution, where we're taking problems like that one there, that doesn't even have any trig in it, and we're introducing trig into it because it actually makes life easier. And then you end up with those trig integrals like we were doing last time, and there's some problems where you're doing a trig substitution and a trig integral and another u substitution, so it gets a little messy. So you might feel like crying, but there's no crying. Do it inside your little head. So you'll be alright. You'll be alright. Sometimes it just feels like crying, it makes you stronger, right? Okay, so I'm starting on the notes on page 39. Trig substitution, page 39, I didn't write it up there. Page 39. Before we go into the notes, a couple things I put on the corners of the board. A little reminder of some of the derivatives that I'm not going to write probably after today, because we hopefully have seen them enough that we've got them up here now. And then over here I have a couple of the identities. And these are what we really need for today. We need both of these, but we also need them in another format. For example, I could take that first one and rewrite it as 1 minus sine squared equals cosine squared, right? I'm just subtracting the sine squared over here. Or what if I want to do secant squared theta minus 1? Just rearrange those. If I rearrange this one, secant squared minus 1 equals tangent squared. So these guys right here, these last three, they're all really the same identity in disguise, are our reference points for today. I will give you those on an exam. Actually, I'll probably give you this one, but you can rewrite it that way. But we want to be able to take those and compare them to the problems we're working with. So those are our big reference points for today. You'll see as we start going over. So the first example on the top of page 39 looks like this. And my question is, can we use u substitution to do this? Why or why not? You're thinking, that's good. Okay, let me ask another question. If you were going to try u substitution, what might you try for your u?
1 minus x squared.
Probably the 1 minus x squared. Let's just go ahead and try it if we don't know. Everyone agree?
Yeah.
That's the inside. We would try u equals 1 minus x squared. And then du would be negative 2x dx. And does that help us or not?
No.
Why not?
Because
the du is not
the
minor.
du,
Yeah, that du is not in here anywhere. I can change this to a square root of u, but I need an extra x in there for my du. If there was like another x out front, maybe I'd be okay. You see the problem is this guy right here? The constant I'm not worried about because we can multiply and divide by constants. But there's an extra x here that's not over here. So this one won't work for you, so we're kind of stuck with this one. I don't think I could do integration by parts either. You'd have to do a u and a dv. Maybe that whole thing would be your u, but then it'd be just a mess. We did a chain rule. So the techniques that we have so far, we're kind of stuck with something like that, even though it looks fairly straightforward. This is where we're going to enter the trig substitution. We'll go back and do that one in a little bit. So right underneath that question, that's my little paragraph there. When we have radicals, I have to say it's not always radicals. Sometimes it's fractional exponents. Sometimes it's not even any exponents, but you will have things like x squareds in them, minus ones, plus ones, maybe minus or plus a 4, plus some constants. And then in that same paragraph, I've listed those same identities over there. I put them with x's instead of thetas, but it's the same idea. So if you have things with a 1 minus x squared, or a 1 plus x squared, or an x squared minus 1, any of those, we're going to match up to those identities. And then the key is in that paragraph, is to draw a triangle that represents your substitution. I'm going to show you what I mean when we start doing the problem. A lot of people forget the triangle and then can't finish the question. I'll show you what I mean by a triangle. So I'm going to actually go through and do this problem now. My question for you is this 1 minus x squared, which of these identities over here is it similar to?
1 minus sine.
1 minus sine squared. Right, we agree?
yeah.
So I'm going to make that substitution. I wish, here's my little I wish, instead of x squared, that I had sine squared. Right, don't you wish I had that because then I could simplify it using that identity? Everyone okay why that's my wish?
Yeah.
So then what am I going to let x equal then? So I'm going to let x equal sine theta. If x squared is sine squared, I'm going to let x equal sine theta. This is the substitution I'm going to make. So the problem, I'm going to make this 1 minus sine squared. I feel good about this. This has a dx in it. So I need a dx. If this is my x, what is dx going to equal? Cosine theta d theta. Before I go any further, I'm going to show you what I mean by the triangle. If x equals sine theta, let's bring it over here. That means that sine theta is x over 1. Right? I just made it into a fraction. The reason I made it into a fraction is go back to your trig memory from before you met me. When you have a right triangle, let's say an angle right here, what is the sine of that angle, sine of theta? Say that again? Opposite over hypotenuse, he says? Remember that before you met me, or maybe you went and watched the online video? The opposite over the hypotenuse must be x over 1. This just came from the x that we chose. We chose x to be sine theta, which means the sine of theta must be x over 1, opposite over hypotenuse. So far so good? Can we find this side? An expression for this side? Yeah, that was very hesitant. Hopefully.
1 minus x squared.
Oh, you're close. Almost 1 minus x squared.
Square root of 1.
Square root of it. There you go. I'm going to call it b just for the moment. X squared plus b squared equals 1 squared?
Yeah.
Pythagorean theorem. X squared plus b squared equals 1. If I'm trying to solve for b, now you see where Ilya got the square root? He says b equals the square root of 1 minus x squared. So I'm going to put that right here. You don't really need to leave the b in there. I usually erase it once I find that other side. Now I have my three sides. There we go. You're probably wondering what's that triangle for? It's to help us write our answer when we get to the end of this problem. So we don't need it yet, but this triangle always comes from the substitution that we made. Okay, so now that we're making these substitutions, let's plug everything in over here. I have an integral. I'm not going to write 0 and 1. We'll talk about that in a minute. Square root of 1 minus sine squared theta. Right, because x is equal to sine theta. And what's dx?
Cosine.
Cosine theta d theta. So dx is going to get replaced by all of this. Dx. Cosine theta d theta. So I substituted my dx and I substituted in my x. What kind of value should go here? And why aren't they 0 and 1?
Because
They have to be thetas, right? This is a d theta, where now we just changed the problem into thetas. If this is a theta, this needs to be a theta over here, and this needs to be a theta over here. These up here were x's. This was an x equals and an x equals to begin with. Those were x values. So now we're going to go have some fun and do some more trig and change them into thetas. Using this same substitution that we made. Let's start with this bottom one. If x equals 0, then we have 0 equals sine theta. What angle has a sine of 0? Sine of what equals 0?
0.
0. Okay, that one's good. We could have got lucky on that one. If x equals 1, this is asking what angle has a sine of that equals 1? Pi over 2. Remember the other day when I said you need to just know your trig? Today's the day. What are those? Those are my bounds. Those are my new bounds here. So 0 now still a 0, but now it's theta equals 0. And x equals 1 became theta equals pi over 2. So all of this is just, we actually haven't even done any calculus yet. We're just, well, maybe we did right here. We took a dx. I lied. A little tiny bit of calculus. We're just kind of substituting everything in, changing everything into thetas. So when I simplify this, what is 1 minus sine squared? Cosine squared over there in the corner of the board, right? Remember I put them up there and said make sure you reference those? So this is the square root of cosine squared theta times another cosine theta d theta. What's the square root of cosine squared? Just cosine. 0 to pi over 2. This is cosine theta times another cosine theta. Cosine squared, thank you. Before I go any further, I want to point out, those of you who have been a little lazy about writing your dx's or your dy's or your d thetas, if you don't write it here, you will forget to make this substitution here, which will change the whole rest of your problem. So please make sure you write down all the necessary pieces so you don't get lost. Okay, we agree with Joseph, that's cosine squared? Uh-oh, here's a review problem from last time. What do we do when we're integrating a cosine squared?
1 plus cosine 2 theta over 2.
Perfect, it's using that identity, which I should probably put over here. One of the identities we had last time, we're going to need them both again today, so I'll remind you of those. 1/2, 1 plus cosine 2 theta, which is the same thing which Chad just said. He said 1 plus cosine 2 theta over 2, and sine squared. Those are those reduction formulas. Remember when we started, I said we're going to do some trig sub, and then we have to use the stuff we just learned about trig identities. So here we go, we're doing that next. So I'm gonna replace my cosine squared with this identity. You don't have to memorize these. If you use them enough, you'll memorize them. That's why I have them up here, because I use them all the time. So I'm gonna pull the 1/2 out front. And this will be 1 plus cosine 2 theta, d theta, from 0 to pi over 2. Okay, with that, I pulled the 1/2 out front. I think we're ready to integrate. Finally. Finally. I might have to go to the next board. I'm trying to make it fit here, but I don't think I'm gonna make it. 1/2. What's the integral of 1?
Later.
Theta, right? Because we're doing d theta. It's not an x this time, so it's a theta. Now be careful here. The integral of cosine 2 theta?
Down cosine 2 theta.
Say that again?
Isn't it 2 cosine 2 theta?
Not quite.
Cosine 2 theta.
The integral of cosine is,
1/2 cosine to theta.
there's going to be a 1/2. But first, if you integrate the cosine, that's a sine, right?
Yeah.
So that's a sine 2 theta. But it's 2 theta. I said it, but didn't write it. But because the derivative of the inside is a 2, you have to divide by that. That gives us a 1/2 out front. That's what we call either the reverse chain rule, or you can call it a mental u substitution, or if you have to, do a little u sub and let u equal 2 theta. And then we'll need to evaluate that from 0 to pi over 2. I'm going to go to the next board because it's all getting squished. If you're not sure about this, stop and take the derivative of it. Use the chain rule and see if it comes out to be cosine 2 theta. That works too. You want to get proficient with your u subs. Okay, so I'm going to distribute my 1/2, and I'm going to evaluate. So I have 1/2 theta plus 1/4 sine 2 theta evaluated from 0 to pi over 2. Warning, make sure you plug your zeros in when you're evaluating trig functions. They're not always equal to 0. Like if I take a cosine of 0, that's equal to 1, right? So some people just don't plug in 0 because they think it will all go away. It's not always the case. 1/2 times pi over 2 plus 1/4 sine of pi, because I took 2 times pi over 2.
That's it.
Yeah.
Minus 1/2 times 0 plus 1/4 sine of 0. Now what I got here, what did you say, Chad?
There.
He says that's 0, sine of pi is 0. This guy is 0. 1/2 times 0, that's also 0.
That one's.
That one's also 0, that's nice. So all I'm left with, I have a 4. That's my answer. It's a lot of work to get a nice little simple answer of pi over 4. I didn't use that triangle I told you had to have. Still sitting there waiting. So you need to have this triangle.
You gotta convert it back.
Yeah, you only need it when you have to convert back to x's. If I had an improper integral, an indefinite integral, where I didn't have the bounds, then I'd have to go back into my x's. That's where that's going to come in. So you'll see it probably in my next example. It's good practice to always have it there. Anybody recognize the original function? Y equals the square root of 1 minus x squared. Anybody know what that is?
Is it like a half circle?
Yeah, a half circle, he says. If you square both sides, that's x squared plus y squared equals 1, which is the equation of a circle with radius 1. But why is it only a half circle?
We're looking at positive values.
Only positive values, right? Y equals positive square root. It's only the top half of that circle. So So there's a picture, and then I'm integrating from 0 to 1. From 0 to 1. So I'm only integrating this portion right here. This blue piece right here is the area that we were looking for. A quarter of a circle. What's the area of a circle?
R squared?
Pi r squared. So in this case, pi times 1 squared. And I want a quarter of that circle. Guess the area is pi over 4. Sometimes geometry is easier than calculus. If you didn't notice it though, how would you know to go that route, right? We knew it was a circle. They won't all be circles either, so. Same answer, that kind of makes sense why it came out that way. Nobody's crying yet? This is good? No crying today, right? All right, so let's go on to the next one. My first example, this was just a warm-up, right, to make sure we understood the concept. So example 1 is pretty messy. Example 1 has a nice radical in it, and some other x's, and does not have bounds, so we'll need our triangle that time. I'm actually going to leave this picture right here and label it in a minute. Okay, example 1. The integral of the square root of x squared minus 1 over x to the 4th dx. As soon as I see the combination of radicals and things squared underneath there, that's what tells me it's probably a trig substitution problem. The first step is again to go over here and try to match up to one of these formulas. In that case, I have x squared minus 1.
Secant squared minus
So secant squared minus 1. Right, the secant squared minus 1 matches up. Everyone okay what I mean by matching up?
Yeah.
So my substitution is going to be that x equals secant theta. That's my first setup here is x equals secant theta. X equals secant theta. To draw the triangle, I'm actually going to change that to cosine theta is 1 over x. Look at me doing a trick there in my head. Right, because secant and cosine are reciprocals of each other. I think better in terms of cosines, that's why I changed it, because I want to draw my picture over there. So if the secant is x, the cosine is the reciprocal of that. Cosine represents adjacent over the hypotenuse. And then if we use the Pythagorean theorem again, a lot of times it's easier to do it in your head. If this squared plus this squared equals that one squared, we'll take x squared minus 1 to get the other way. X squared minus 1. If you need to write out the whole Pythagorean theorem, you'll get that same answer. Notice that that radical matches this one. Warning. Don't just write down the one that you see here, because if you made the wrong substitution, it won't be correct. A lot of people say, oh, I know it has to be that one. Only if you made the correct substitution, to make sure that it comes out. So use it as a check, not an assumption. Okay, so there's my triangle, which I'll come back to in a minute. I have my x, that's my substitution. What should I do next? Look at it.
Substitute the secant.
Say that again?
Plug in the secant.
Yeah, I can plug the secant in here and here, but there's something else I need, because I need to
You need the.
I need dx.
Yeah.
So I need to find the derivative of it. So once you choose your x, make sure you find your dx. The derivative of secant is secant tangent. Secant tangent d theta. Okay, so let's plug everything in carefully. This up here is the square root of secant squared theta minus 1. Down here I have secant to the 4th theta. Yes?
Just a quick question. Why do you choose
cosine for the triangle again?
Just because most of us know how to label our triangle with sine, cosine, and tangent, and most of us don't think in terms of secant, so I just change it into either a sine, cosine, or a tangent, just because it was a secant to begin with. I personally have to think upside down, so I rewrite it so I don't have to worry about, because some people have secant memorized, that it's the hypotenuse over the adjacent. I don't have it, I only have the 3 memorized, so I flip it first. Does that make sense? Okay, so I still need to replace my dx. Dx is all of that. Do not forget to put all of it in here. The biggest mistake people make is they just change the x into a d theta.
You forgot an extra thing.
Oh, thank you, I'm missing one. You try talking and writing at the same time, it's hard. Here we go. So the biggest mistake is people just write d theta, but make sure you put what dx equals. Okay, let's see what we have now. What's secant squared minus 1?
Tangent squared.
Tangent squared is why we set it up to match our identity over there. So that's tangent squared. I have secant to the 4th on the bottom. And I still have a secant theta, tangent theta. And square root of tangent squared is tangent. This is the whole reason we do this trig sub, is to get rid of those radicals. The radical is gone now. So I have tangent theta on the top, secant to the 4th on the bottom, and another secant tangent. Still with me? Got lots of nods, that's good. So one of those secants will reduce. Right, this one will reduce and make that one a 3. Combine the tangents. So I'm seeing tangent squared theta on top and secant to the 3rd theta on the bottom. Putting everything together. Alrighty. So we've succeeded in doing the trig substitution, and now here we are with the trig integral. It's like starting all over again from last section.
Do you have to put some like in terms of sine and cosine and?
Exactly. Whenever you've got these fractions and not just secants and tangents multiplied, it's almost always better to change it in terms of sines and cosines and see what simplifies. It's only when you have like our quiz today, which were tangents times secants, that you could probably leave it that way. But in this case, it's best to switch them around. So let's use that identity. I'm going to bring it down to this next line over here. That is sine squared over cosine squared. That's my tangent squared, right? Lost my integral. Over the secant cubed. Yeah. 1 over cosine cubed. The messy fractions inside of a fraction. Here's tangent squared on top. Secant cubed on the bottom. Dividing by a fraction, though, is the same as multiplying by the reciprocal. So let's rewrite that and make it prettier. Sine squared over cosine squared times cosine cubed over 1 d theta. Right, multiplied by the reciprocal. You see those cosines are going to reduce?
Yep.
All of these are gone, and this is gone. I only have 1 cosine left. So I now have the integral of sine squared times cosine theta d theta. All right. Now we're back to the beginning of the trig integrals section again. I need to make a substitution here. Another, so make sure you realize it's another substitution. I already changed x's into thetas. Now I have to change thetas into something else. I want to know what should I substitute, and I want to know why. Who wants to tell me what to substitute and why?
Made sine of theta u,
Okay, why?
because derivative of it is cosine.
Gorgeous. You guys all hear him? He says let u equal sine theta, because the derivative is cosine theta. We have one extra cosine hanging around here. That's our derivative. So he says, let's let x equal sine, u equal sine theta. Because when you take du, that gets rid of all this. So this part right here is the du. What's this? U squared. Oh, we can totally do this. I'll bring it up in the next board though, so I'm still gonna squeeze in the corner again. So I now have u squared du. That's the whole thing, right? This is my u squared and that's my du. Look how pretty it is. I think we could actually integrate it now. We spend 20 minutes getting ready to integrate what we do. We use trig and algebra. The integral of u squared is
1/3 u to the third.
1/3 u cubed plus c. Don't forget that plus c. Am I done? No.
Plug sine back in.
I can't even, I have to put sine back in, then I eventually have to go back to x's. Remember, the problem started with x's. We changed them to thetas, and then we changed it to u's. So now we have to go back to thetas and then back into x's. We can do it, and we're not going to cry. We can do it. So we're going to put the sine back in there. We agree that's 1/3 sine cubed theta plus c. Here's where the triangle comes in. So we went back and we now have thetas, but it's not really obvious how to get back into x's because this was our substitution right here. We said x equals secant theta. It's like, how do you change that into sines? So this is why we draw the triangle. This is a picture of x equals secant theta. I want to find the sine of this theta. The sine of this angle is the opposite over the hypotenuse, this square root over x. That is the sine of this angle. That's why we drew the picture. So we're going to write it as 1/3 times that square root over the hypotenuse cubed plus c. I want to make sure everyone see where this part came from. This was the opposite over the hypotenuse from our picture here. If you were to check out my answer on the answer key, it would probably look something like this. But I wouldn't even have the 1 down there. It would have something like this. I would accept that answer, by the way. But it would look maybe something like this. Can we see where I got that? The square root is a 1/2 exponent. So that's to the 3/2. The x is just cubed. This 3 was in the denominator, so it's still in the denominator. Messy. But doable. Messy but doable. It seems to be my theme for this semester. Questions? Again, organization, organization, organization. If you're not organized, you're not going to get back. If I wanted to take the derivative of this, I would have to use the quotient rule and the chain rule. And I could probably do it. It'd take me a few minutes. What will my answer be if I did this, take the derivative of this correctly?
Should it be the same?
Yeah, it should be this problem over here, right? So for fun, we could take the derivative of that using the quotient rule and the power chain rule. You'll end up with that. Checking our work. You all right? You think?
No.
You're right. It is hard. Other than that, are we okay? Life is hard. You're gonna learn this over and over and over again. It just keeps getting harder too, right? When you think you've got it down, it throws your curveball. Calculus is the same way. Okay, so let's look at number 2. Number 2 is a little bit messier. If you thought that one was messy, number 2 is messier. Okay, we're good. Let's start over here for number 2. Let's see if I can fit it on one board. So I have the integral of the square root of 25x squared minus 4 over x dx. Whoa, this one just got way harder. Wait, what? Go ahead and panic a little bit, I'll wait. You already figured it out. He's done panicking already. So why the panic? Why don't we like this one? That 25 is a little weird. 25 is a problem. What else is a problem?
The 4.
The 4, right? Look at my little formulas over here. Do any of them have a 4 in there? Nope. They don't have 25s either, for that matter. But they all have 1s. Every single one of them has a 1 in there. Yes, sir.
X is equal to 2/5 of secant theta.
Yes, so Chad's already figured out what x is going to equal, so hold that thought. He said 2/5 secant theta. I want to show him how to get there first. But I like that. So 2/5 secant theta is what he wants to do. All right, so the problem is, I'm supposed to have a 1 here if I want to use one of those formulas over there. So the first thing I'm going to do is factor out that 4. Now, I can't factor that out, Jill. It doesn't go into 25. Yeah, you can. You just have to be creative and embrace fractions. I'm going to factor out that 4. That would be a minus 1, right? If I factor out the 4. This will be, I guess, squeeze it in here. 25/4 x squared. It's messy, I agree, it's messy. Do you agree that's the same problem? Why did I do that? Yeah, I need to have the minus 1 to match up with that identity over there. There are other ways to get there, but I like to do this way because people can all see where it comes from. So I have the minus 1. So if I have the minus 1,
It's a secant.
it's a secant squared. Remember Chad said he wanted to do a secant. And I wish, here's my wishful thinking again, I wish this whole thing, 25/4 x squared, I wish that was equal to secant squared. Don't you? Then it would be pretty. If this right here was a secant squared, we agree it'd be nicer? If only? So we'll force it to be. Where's the math? Use a strong arm. I'm gonna take the square root of both sides here. So that means 5/2 equals secant theta. Check the square root of both sides. Can you solve that for x?
Yeah.
By doing what?
Multiply by
2/5. X equals 2/5 secant theta. Which is exactly what Chad said a few minutes ago. So they don't always have a 1 in them, but we can make them have a 1 just by being creative with our algebra. Questions up to there? All right, what should I do next? Panic some more? We could do some more panicking if it
Plug
helps.
the 2/5 secant.
Did I hear you said?
Plug in the 2/5 secant theta to that.
Yeah, I could plug this in here. But if I do that, I also need to plug something in here. We have that. But I also have to plug something in here. Oh, I should probably find that then, right? I need that. So dx is equal to secant tangent, but I also have a 2/5 out front, right? So 2/5 secant theta, tangent theta, d theta. So now you want me to plug everything in? You don't want to draw the triangle first? We could do it later if we have to. Let's just skip the triangle. A lot of people forget the triangle, you'll see when you need it, so we'll draw when we need it. Let's plug everything in, carefully. Now, a little warning. You could replace this x with what we just said x equals, this x and this x, right? You could put that in there. But remember where it came from. 25/4 x squared is secant squared. So instead of putting it all in there and simplifying again, that's where it came from, right? So we can just replace 25/4 x squared with secant squared. That's where the whole substitution came from. Otherwise, you're going to have a 25/4 times a 4 25ths, and it'll all go away anyhow. There's my secant squared on the top. Okay, on the top? The bottom is just x, which is 2/5 secant theta. And then the dx is 2/5 secant theta, tangent theta, d theta. It will always get messier and then it'll get better, I swear. If you did the right substitution. So what happens here? Yeah, the 2/5 up here, makes this one go away down here, the 2/5 are gone. What else?
Secant as well.
The secant theta and the secant theta? Yep. What about this 4 in here? We take it out, just a square root of 4. That's a 2, let's bring that all the way out in front.
And then
You guys okay with that? The square root of 4 comes all the way out front as a 2. And then I have the square root of, well, what's secant squared minus 1?
tan squared theta.
Tangent squared. Oops, tangent squared theta. Well, I don't even have a fraction anymore. Nothing's left in the denominator, and then I have another tangent theta over here. And a d theta.
So the squares cancel out, the square and square cancel out.
The square root and the squared will reduce right here. That's the whole reason we do all this. So that's equal to 2 times the integral of tangent theta times tangent theta, d theta.
Combine the theta.
Yeah, go ahead and combine those. That's a tangent squared theta. I don't know how to integrate tangent squared. What'd you say, Lydia? Jamie, did you say something? No? We could try integration by parts, but there's something even easier than that. Even easier than u sub. Ooh, I like where you're pointing over here. Nick's pointing over here. Tangent squared is equal to secant squared minus 1. Why is that helpful?
Secant squared is a derivative.
Because secant squared is a derivative of tangent. We know how to integrate those. Whenever you have just tangent squared, you want to change those into secant squared minus 1. What's the integral of secant squared? Over there. Integral of secant squared is tangent. Gotta know our derivatives. Minus
Theta.
theta plus t. We're getting somewhere. At least we've integrated now. We changed our x's into thetas. We've now completed the integration. I'm not done because the original problem had x's in it, and this has thetas in it.
Do you want me to do it first or?
I I can distribute the 2 now or later, doesn't really matter. I'm gonna bring it down here so I have more room. 2 tangent theta minus 2 theta. Let's see. What do I need?
I need the triangle.
Now I need the triangle. I can't find the tangent of theta without a picture of it. Some of you can. Some of you can think like this. I cannot think like this. I can't figure out what, I can't change the sides in my head. I'm gonna draw a picture. Again, I'm gonna do what I did on that last one. I'm gonna change that into cosines, just because I can think better in terms of cosines instead of secants. Cosine is the reciprocal of secant. So think of it this way, by the way, 5x over 2, right? So what can I say about the cosine of theta?
So it's 5x on the top, Jason said.
Right, 5x is on the bottom then,
And 2's on the bottom.
and 2's on the top, right? Flipping it upside down? Reciprocal? I flip this upside down, I flip that upside down.
Negative 5x.
Now I can draw the beautiful picture. So it's 2 over 5x. Again, you don't have to change it to cosines if you can think in terms of secants. I just don't have them in my head easily. I have sines, cosines, and tangents, and it's easier for me to look at it than to keep it all in my head. But if your triangle is good, I'm happy about that. What's this side? The square root of the hypotenuse squared minus this squared? Hey, look at that. 25x squared minus 4. What a coincidence. What does that help me do? I drew it.
Now we don't use
It helps you convert it back to the
Yeah, it helps me convert back here so I can actually find the tangent of that angle now. Here's theta. What's the tangent of that angle?
Square root over 2.
The square root over 2, the opposite over the adjacent, right?
Yeah.
So 2 times the square root of 25x squared minus 4 all over 2. That's this part. Minus 2 times theta. Uh-oh. Just the regular old theta. What is theta?
Can you try to find R cosine and that stuff?
We could do arc cosine, yeah. We could do, so he's talking about inverse cosine. We could do inverse cosine, we can do inverse secant, but the important thing is that theta is an angle. And you can use inverse cosine, inverse sine, anything you want. Do we all agree that, maybe from here, if cosine theta is 2 over 5x, that means that theta is the angle whose cosine is 2 over 5x. Right, that's what an inverse trig function does. So we could have used cosine. You also could have done from over here. You could have said that it's the inverse secant of 5x over 2. We could have said the inverse sine of this over this. I mean, any of those inverse trig functions would work. But you have to describe the angle. So I'm going to stick with this one since we already had it up here. So instead of theta, we're going to replace theta with inverse cosine of 2 over 5x. This statement right here means the angle whose cosine is equal to 2 over 5x, which is exactly what we have. So anytime you have a theta by itself, you're going to end up having to solve using your inverse trig functions for theta. And this is my answer. It's my, oh, no, I gotta simplify my answer. You see my simplification I missed?
Yeah.
These 2's are gonna reduce. So it's just that square root minus 2 times that inverse cosine of 2 over 5x. You see where I wear my shirt today now? Makes you want to cry just a little bit. Questions? No questions? Okay, let's go ahead and take a break. When you come back, I'll probably do one more with you, then we'll let you guys try some on your own and see how those go. Let's take a 10-minute break.
Joe,
Yes,
is that for one of the quizzes?
just for one of them, yeah. It's the same kind of idea. All right, before we go on with trick sub, I want to do two things. One is I'm going to answer the question Brittany asked earlier about how is it possible that if you do it one way, you get this for an answer, you do it the other way, you get this for an answer, and how can those be the same? Now, this is for one of the quizzes earlier, where depending on if you let u equal tangent or u equal secant, you get really different looking answers. So I'm going to explain how those are actually equal. But before we do that, I'm going to pass something around the room. If you recall, when you signed up for the class, it said we meet, these 4 hours a week-ish, plus 2 hours by arrangement in the math lab. So you actually have to make an arrangement with me on paper. So on this paper, there's a spot for you to put your name and the days and times that you're going to go to the math lab and which location. Maybe you'll go to the Brentwood lab or the Pittsburgh lab, and then you're going to sign your name. I don't care where you do it, when you do it. The only things that have to happen are between 8 a.m. and 8 p.m. Monday through Thursday, and between 8 and 4 on Fridays. And if you make a deal with me, and I put a sample here, you say you're going to go every Tuesday from 3 to 5, and you end up going every Friday morning from 8 to 10, I don't care. All that matters is you make an arrangement with me and that you sign in for 2 hours a week. That's all that matters. Is that clear?
So, is
Yes.
it like, is it the time we have to spend actually with you or?
No, so you're supposed to be going and signing in the math lab 2 hours a week, so you have to pick 2 hours out of your week that you're going to do that. But my point is, you don't always have to go the same time. You just have to choose 2 hours, say this week that's going to work, and then regularly spend 2 hours a week in the lab. It does not have to be with me. The most important thing is, do not have it conflict with any of your classes. Don't tell me you're going to be in there on Fridays if you've got a class on Fridays. Because they will catch that and send it back to me, and I'll have to say, we have to fix this. So they actually audit all of these. So you have to choose a day and a time that does not conflict with the rest of your schedule, and tell me that's when you'll be in the lab. At least 2 hours a week. I'm just going to pass this around. Everyone clear what you're going to do with it when it comes to you? Yeah. No questions? Okay, I'll start over here. Now, let's explain how it's possible that this and that are equivalent. And so I'm going to start with this one and make it look like that one. So I'm going to rewrite this as 1/6 tangent to the 6th x. I'll put the 1/6 out front. And I'm going to use one of our favorite identities from today. What can we do with tangent squared? Can I write this as tangent squared cubed? Two. It's getting worse as I go. Hang on, let me fix my 2. Tangent squared cubed, that's tangent to the 6th? Yep. According to that, our identities over there, what is tangent squared equal to?
Secant squared minus 1.
Secant squared minus 1. So this is 1/6 times secant squared x minus 1, the quantity cubed. Right? So now, I'm going to skip some algebra steps. If you wanted to cube this, you would have to take this binomial and multiply by itself 3 times. Or if you know the shortcut that's Pascal's triangle, if you don't know it, come see me in the lab or talk to me after class. I'll show you a nice shortcut for cubing things. You will find out that when you actually spend the time to multiply that out, you will end up with secant to the 6th x minus 3 secant to the 4th x plus 3 secant squared x minus 1. So if you have to spend some time, I just used a nice shortcut. If you don't know the shortcut, you want to come see me. Because I can't multiply that in my head, but I know the shortcut in my head. And now I'm going to distribute through my 1/6. So that's secant to the 6th x over 6. Oh, I forgot. I'm still working on it. We're good. Minus secant to the 4th x over 2 plus secant squared x over 2. You guys see that because the 3 and the 6's are reducing?
Yeah.
Minus 1/6. So I claimed that this expression or this expression were the same. Are they?
Yeah.
Is there anybody who's hesitating with that yet? There's a part that it doesn't match.
The minus 1/6.
That minus 1/6. But remember, there's a plus c right here. And there's a plus c right here. So if I add a plus c to this one, and a plus c to this one, 1/6 is a constant also. So a constant minus 1/6, this whole thing is just a plus c, plus a constant. So they are equivalent. Blows your little mind. Does that answer your question? And they look totally different, it just depends on which way you started. Interestingly enough, if you were doing this problem, say on WebDesign, it would know to take this one or that one, because it knows that you might make one substitution or the other. A little fun with trig. If we weren't already having fun with trig. A little more fun with trig. Okay, example 3. I'm gonna do example 3 with you, and then you guys are gonna try the practice problems on the next page, see how we do with those. Make sure we have this down, because it makes sense when I walk you through it. Example 3. The integral of 1 over x squared plus 1 dx. The whole thing doesn't even have a radical in it. Doesn't even have a radical. What do you think I should do? Oh, sorry, I'm blocking the thing here.
Change it x squared plus 1 to 1 plus tangent squared.
Yeah, 1 plus tangent squared, he says. 1 plus tangent squared. We have 1 plus x squared. So what's my substitution?
Done.
X equals.
X equals tangent theta. X equals tangent theta. Because I've got 1 plus x squared. Now what?
So you're gonna find the
We
dx.
need dx, yep. dx equals
Secant squared.
secant squared. Let's plug all that in. 1 over tangent squared theta plus 1 times secant squared theta d theta.
So we'll cancel out.
Yeah, this is gonna end up being a secant squared, right? That's why we chose it. And then, it already sees it's gonna reduce. This is a secant squared down here. This is a secant squared up here. Everything cancels out. What am I left with?
1.
1. The integral of 1
Just wait.
d theta. What'd you say?
Wait.
So just be theta, right? Can we integrate it?
Yep.
The integral of 1 is just theta plus c. What is theta?
Tangent of x.
Arctangent or inverse tan of x plus c. Remember, that's what this statement means. If x equals tangent theta, then theta is the inverse tan of x. We've got to get going back and forth. We're done. Do you guys remember last week? We were taking the derivative of the inverse tan, and I said, you want to memorize this because it's going to keep coming up? Anybody remember what the derivative of that was?
X squared.
Maybe it looked like this,
1
1 over 1 plus x squared, right? And that should make sense, because if I take the derivative of this, I should get back to where I started. And when I integrate that, I get inverse tan. In the future, anytime you see this expression, you can just write inverse tan. You don't have to go through the whole trig substitution. But if, by chance, you forget it and don't recognize it, like I was telling you last week, you want to recognize it, you can get there with some trig substitution. But we're going to be seeing that one quite a bit Thursday. And we're just going to take a shortcut and go straight from there to here from now on. Questions? Okay, so we still have, what, we have 45 minutes left almost? All I want to do is have you guys work on the two problems on page 41. There's a typo on the first one, so make sure you get that correction before you make the work.
What's the typo on the first?
See if we can get those answers, and then if you happen to get both of those done, then you might want to start working on your lab assignment now too, while you've got me here to point you in the right direction and make sure everything's clear. So let me tell you what the problem is, because there's a typo. Practice problem number 1 on page 41. It should have a fourth of the denominator. 1 plus x squared over x to the 4th. You guys see that 4 is missing? At least it's missing on mine. I don't know if we corrected it. And then the second one is okay. So I want you to work on that problem and on this problem. Square root of x squared minus 1. See if you can get my two answers. Work together, ask for help. Ask for you to point yourself in the right direction. It might take you 20 minutes, I don't know, maybe more. I'm okay with that.